Hello, guys. Good afternoon, everybody. So today we will talk about clustering algorithms. So if we put this chapter under the bigger picture of machine learning techniques, we can say that this is clustering algorithms belongs to the realm of unsupervised machine learning. And the biggest difference between unsupervised methods versus supervised method is that whether we make labels, whether we create labels for the data points. So far, most of the models we have covered in this course are for supervised machine learning models, which is that given some data, we want to have those data labeled with some, like the features associated with the Y's, and Y is the ground truth label, right? So that our models can learn the mapping relationship between the X and Y. Okay, but for clustering algorithms, for unsupervised machine learning, we are dealing with cases where for the data we don't have ground truth labels, and the task is really not to learn the mapping relationship between X and Y's, but to describe the patterns in the data, in the feature in X alone, right? We don't need to use labels, right? We don't have labels to study about the data. Okay, so clustering is one of the most significant, most useful algorithms once we have some data to explore with. Okay, so let's see. We will not have time to cover every piece of details for all the algorithms listed here, but we will start with k-means, and for k-means we will spend most of the time into it, talking about the details about some issues with it and how to overcome it, right? So I would encourage you to, after the lecture today, I would encourage you to go through the slides carefully, especially about hierarchical clustering and the density-based methods, which we will not cover every piece of detail in the lecture today. But you will see that the way that I present the algorithm in this way is that the algorithm is basically getting improved in terms of getting better clustering outcome. Okay, so what I hope to do today in the lecture is that we should cover k-means, right? We can talk a little bit about these two algorithms, but I also wish to draw some comparisons with the mixture Gaussian model with the k-means. And these two can be basically seen as related algorithms, but the mixture of Gaussian models is more of a, more advanced versions of k-means, which relies on basically Gaussian models. And we will see the connections between the two and the advantages of having a mixture of Gaussians over k-means. All right, that is the plan for today. All right, so a little bit background about supervised learning is that we know the labels. So in this example, we know the data points that cluster to the left, the groups in the left clusters, they have the cross and they are in the blue color, right? On the right, we have circles in orange color. We know that these examples are the second class of data points, right? But if we don't have that information, say we don't have labels for the data, then it is a totally different learning task that we are dealing with. Okay, so before, without the label, we want to see how the data naturally distributes, which is that whether we can find some patterns that can be observed within the data itself, like whether there are patterns in it, whether there are structural information about the data. And the simplest pattern that we usually first look at, given some unlabeled data, is that whether they groups into different clusters, like whether we can find that some of the data, they are closer to each other, right? Like those data points towards the left, they are closer in the feature space, right? So that it's possible that we can think of them as one potential class, right? While at the same time, the other data points, they are closer towards each other in the feature space, which means they can be thought of as a second kind of data classes. Okay, all right, and so the task here becomes to find the clusters among unlabeled data points. So the clustering algorithms are actually everywhere in our daily applications, like the Google News. I don't think, I'm not sure if it's still online or how popular it is, but it's basically use text clustering services. I mean, text clustering algorithms to group of the news articles published in the world into different categories. Okay, because there will be no human judges to text, like to label each category to each article into the available categories of text. Okay, and it's also useful in image processing. Like you can use a k-means, run the k-means on the pixel points, on the pixel data of the image, so that the pixels that are closer in terms of RGB values or grayscale values, they are kind of grouped into the same cluster. Okay. All right. So we will start with a example of k-means by looking at a series of slides with colors annotated. Okay. So this k-means is actually has been there for a pretty while, for a pretty long time. It's first developed in 1967, right? It's actually, the algorithm was first proposed even earlier than that. Okay, so we will use this example to showcase how the algorithm runs on the simple 2D space data sets. Okay, so we assume that all the data points we have, they have two features. You can think of the x-axis and the y-axis as the two features. And if we plot them in this 2D space, we can see apparently a very salient clustering patterns, right? But how do we let a computer program to discover this pattern? Like how do we assign a cluster label to each of these data points so that the data points that are closer towards each other are assigned with one label, while the other group of data assigned with the other label. So these are some details that we need to go through here. So the goal is to assign all data points to two clusters. Okay, so this number 2 here is totally empirical. Like after plotting data into the 2D space, we can like have an estimate of how roughly the data may look like in this 2D space, right? So that's how we decide that we should assign data points into two clusters. Okay. Otherwise, if there are another group of data around here, right, which is equally far apart from these two clusters, then we should probably say that we should assign all data points to 3 clusters instead, right? That's totally based on empirical observations. Okay. So in this simplest case, we have 2 clusters. So what we're gonna do in the first step is to pick 2 random initial cluster centroids. Okay, so a centroid is a point in the feature space that represents where the center of a cluster locates. Okay, so this centroid point can be one of those data points, or it can be a can be the average of all the data points, which is a imaginary point, which is not one of the actual data points. Both ways are okay, right? So let's just pick two random initial cluster centroids. Okay. So in this case, we just randomly select some points in the space, in a feature space. Okay. And then the second step is to paint the data points that are closer to the red, centroid into the red color, while at the same time the other data points that are closer to the blue centroids with blue color. Okay, so you see, if we use the Euclidean distance, for example, right? All the green data points, if we separate them in terms of their distance from the two centroids, then you can see that the right half becomes all blue, right? Because they are closer to the X data points, and the left half are all red because they're closer to the red centroid. And apparently this is not ideal, right? It's not recognizing the clustering patterns that we human beings has perceived, but it's okay because it's an algorithm we should run for multiple times. Okay, so the step 3. Okay, after we have painted the colors for all the data points, then what should we do next is to compute a new position for the red centroid by computing the average of all the current red points. Okay, you see, we have that many red data points, right? We should compute the average positions of these data points and use that average position as the updated position for the red centroid, which is very likely to be different from this original one. And similarly for all the blue data points, we should use the average position to update the blue centroid. All right. Okay, so say after step 3, the new positions of the centroids move to the current position. All right, so they are closer to the majority of the data points for each color, right, respectively. The blue one is closer to the majority blue ones, and the red ones is closer to the red majorities. So after the centroid is updated, what we're going to do is simply to repeat these step 2 to step 3, right? Which means now we need to repaint all the data points because now the centroid has moved. So we need to recalculate the distance for all the data points from those two centroids. And then we decide which centroid those data points are closer to, right? Say now, for example, these, if I mark them as a, with a red pen, these data points here, right? They used to be in red, right? But now if we calculate their distance to the blue centroid, now they are closer to this new blue centroid. So after we repaint their color, it will be to into the blue color, right? And so is the data points down there, which it was used to be blue, and now they are painted to red. Okay, so and then we need to update the positions of the centroids again because we need to do that because there's some change in the data points, right? So here's the new centroids, and after that we repaint data points and recompute. Okay, so you see at this step we will repeat all the step 2 to step 3 until that there are no more points need to be repainted. Okay, so for example, after this point, if we calculate the distance for all the data points to each centroid, we see that all these data points are in the right color because they are closer to the blue centroids and they have already been correctly painted to blue. And for these parts, they have all been correctly painted to red. So in this step, we say the algorithm simply needs to terminate because it's already converged. We have find a stable positions for the centroids. Okay, so that means we can use those centroids, the stabilized the centroid positions to indicate the positions for the clusters. Okay, the blue cross says the positions of the blue cross and the red cross represent the two clusters in the data sets. Okay, and we're done with the k-means. So yeah, that's pretty much a straightforward demonstration of the k-means algorithm. Okay, and that's a animated demonstration. And if we want to give a formal definition, then we can also use the language of machine learning. Use the language of optimization problem, for example. Say, given the data sets, we have x1 to xn, right? They are from the n dimensional, and which means each data point is as an n dimensional vector. And we want to group the data into k clusters, okay? So these are a more general values here. Okay. So what we need to do is to initialize k cluster centroids, right? So which are actually k vectors representing the centroid location, right? So we need to repeat the following code until convergence, okay? And within the body of this code, there's actually two parts of the code. The first part will need to compute the new positions for the centroid. We need to compute. We need to decide which cluster, which cluster that each data point should belong to. You see, so this C of I, this is a variable to determine the i's data points should belong to which centroid, right? It finds the j's that minimize the distance from that data point to the j's centroid, the centroid j, right? So we need to assign the j to the centroid to each data points so that the distance is minimized. And then after we have updated the so this step is kind of to repaint, okay? So it's the so-called to repaint the data points. And the next step is to update the positions for the k centroids, right? So this is a for loop to go through all centroids, and the new positions for the centroids will be the average of the position, or average positions of all the data points in that cluster, okay? That is the more formally defined k-means. Okay, and usually we will use Euclidean distance as the measurement, but we can always use different metrics, okay, in terms of distance measuring, depending on the nature of the data. Okay, so if we want to say from a machine learning perspective, use the terminology of cost function, then we actually is minimizing this cost function, which is described by the distance between each data points to the corresponding centroid position. So after the algorithm converged, that this distance measurement is minimized, okay, and it's actually guaranteed to converge, which is a very good news, which means that for basically given any data sets, and you can decide the value for k as you wish, right? You can select 2, 3, 4, whatever k values you have, and the algorithm is guaranteed to converge, okay? Some k values may not be the proper number, but you will always get some clustering results. But it's the post-hoc analysis that needs to be used to evaluate how good a clustering result is. Okay. So there are some practical issues we need to carefully think about before using k-means. So the first one is to how do we initialize centroids? Okay, so we can, several possible ways are there. So it's like, first one, we can randomly pick k data points as initial centroids, right? If we have a lot of data points, then we can just randomly pick one, okay? And but sometimes a different initialization will lead to different clustering results, right? So if unfortunately the selected data points, they're very close towards each other, then it is not, then the clustering results will be not ideal, right? Because the centroid position you choose are just not representative of the general clustering patterns, right? So for instance, if we have some data points like this, and we select the blue, the red, and the yellow data points as the centroid, and use that to initialize the k-means, then probably after the algorithm converge, we will have 3 clusters like this, right? But if in the next round, we select the centroid, initial centroids differently, then the results might be different, okay? So like the 3 clusters result in the second one is totally different from the first one. So which means that the k-means is pretty sensitive to our initialization condition. And in practice, we can run multiple times with different initializations and then evaluate the clustering results, okay? And then another solution, which is called k-means plus plus, which is actually provides a more stable way to select the initialization positions for the centroids, okay? So let's quickly go through this. So for this k-means plus plus algorithm, it will choose one centroid uniformly at random, okay, from data points. So it's like we draw from some uniform distribution. Each data point has equal chance to be selected, okay? So before selecting the next centroid, what we will do is to, for each data points, we will compute a distance measure, which is the distance of that data points. That distance measure measures the distance between the data points and the nearest centroid that has already been chosen. Okay, so given that distance computed, we need to use that distance to alter the probabilities of choosing the next data points, right? So we need to choose one new data points at random as a new centroid, but this time the probability of choosing a data point X is proportional to the distance, which means among the remaining data points, if those data points are farther away from the current centroids, then they will have a higher chance to be selected. Okay, so I think that's a algorithm that makes sense, right? Because we want the centroids to be, farther away from each other. Otherwise, you're gonna cluster too close towards each other. Okay, so that is the main principle of selecting the next new centroids. Okay, so we will repeat the steps until the k centroids have been chosen. All right. For instance, when we have selected the mu1, which is in blue as our first centroid, right? And since that's the above group has higher chance to be choose mu2 because they are closer, they are farther away from the mu1. Okay, and then after mu2 is chosen, then the bottom right group of data will have higher chance to be chosen as mu3 among these data points. Okay, so which empirically speaking, it makes more sense as it encourages the centroids to be farther away from each other. Okay, all right. And we have another practical problem question about how to choose the k. Okay, that is also a practical problem because so far our selection for k is purely empirical. Like we observe the data, the distribution of data, and then we select the number. Like we determine how many clusters there should be based on our observation. Okay. And that is true, and that works out for most scenarios. Oops. Right. So like for example, in this case, when the data only have one, we may see that it's just one group of data points, which just don't separate into, don't have a very significant patterns of clusters. So in those cases, we can probably selecting one is more reasonable, right? And in this case, in the second case, if we select 3, then it's not just as reasonable as selecting 2, because it seems that there are 2 clusters in the data points, right? So we actually need to use some more objective standards, objective measures to evaluate the results of clustering. So for example, use the right part as an example. Say if we want to know whether k equals 2 is better than k equals 3. Okay, so we need to come up with some metrics that shows that the k equals 2 is a more reasonable choice. Okay, so that's what we will show next to talk about the evaluating methods for clustering results. Okay. All right, so a general principle that we can take is that a good clustering algorithm should result in a higher similarity within the clusters. Okay, we want if a group of data points are assigned within one cluster, then we want the similarity between those data points are higher, and the similarity between clusters, between 2 different cluster groups are lower. Okay, so these high and low are just relative standards. Okay, so based on this principle, people have proposed the silhouette coefficients, and it's a French word for contour or outline. Okay, so it's basically a ratio, a ratio of 2 numbers. The numerator is the mean distance b minus the mean within the mean distance a, and the b, meanings of b and a is that b is the mean distance between the data points and all other data points in the next neighboring cluster. It's kind of the measurements of the between cluster similarity. Okay, and the a here is the kind of the within cluster similarity here. Okay, so if we want the high similarity, we want the within cluster high similarity to be as high as possible, right? And also the between cluster similarity to be as low as possible. So we basically should have we want to have lower silhouette coefficients with when we evaluate the results of k-means. All right. So for example, in the example here, our data points look like this, right? We have several data points here and several data points here, right? When we use k equals 2, right, it will be a difference from k equals 4, okay? But so far, I didn't see a significant difference here, right? I don't think it's a good example. So if we are interested, you should follow this link to see how the silhouette effects, how our silhouette scores can be used to analyze to evaluate different case on the same data sets, so that the more reasonable case would have a better silhouette score. Okay. All right. So we're pretty much done with the k-means algorithm. Its pros and cons are pretty straightforward to see. First of all, it's very easy to implement, and it can scale to very large data sets. Okay, but the cons is that we have to decide the k empirically, and sometimes it's not an easy job. Okay, and another significant con is that disadvantage is that it only works for spherical and convex clusters. But if we have some complex, it's more sophisticated clusters like this, like there's a convex clusters or two rings, then it will generate some results that are not, as we expected, right? If we, based on, like if we want some clustering results based on connectivity, say, if we want the inner ring to be clustered as one cluster, while the outside ring to be clustered into a second one, then k-means will basically disappoint us, right? Because it's based on pure distance, but it's not on connectivity. So it will only consider that if we initialize our centroids in these two positions, it will consider the right half to be closer to the right centroid, and the left half closer to the left centroid. So it will not be able to generate the results as we expected in these cases. Okay, so that's why we will have to introduce other clustering algorithms. Okay, but we will not introduce the hierarchical cluster for now. Let's go to the last item on our list, which is the mixed Gaussian models. Okay, okay. So the reason why I want to talk about mixture Gaussian model is that we have it is closely related to the k-means, and we will see how different they are. Okay, so a little bit review about the k-means. Okay, it will make hard assignments to data points, right? Each time we need to decide for each data point, we want to decide that it must belong to either one of the k clusters. Okay, but that is sometimes just too arbitrary. Sometimes it's not ideal because there's ambiguity in data points. Sometimes a data point can belongs to it can have the possibility to belong to multiple data points, multiple clusters, right? So for instance, like if we have a cluster of a distribution of data points that look like this, then if we think of it as a mixture of two distributions, right? The two ellipses, they are kind of the contours of two Gaussian distribution, two-dimensional Gaussian distributions, right? So we can think of it that we have two Gaussian distributions that generate the current distribution, the current mixture of distribution. Okay, so it looks like more reasonable that the clusters may overlap towards each other, which means it's sometimes just too simplistic to make hard assignments, and we actually calls for a more soft assignments, which means that for each data point, we should assign a data point a probability that it belongs to each cluster. Say in this case, the data points here, right? It may have a 50% being the blue color, while 50% being a orange distribution, right? But for this one, it may have higher probability to be to be an orange distribution rather than the blue distribution. Okay, so let's see how that can be accomplished. Okay, so first of all, let's review the mathematical concepts of Gaussian distribution a little bit. And a Gaussian distribution, so Gaussian is just another name for the so-called normal distribution in statistics, right? We can use this n with some mu and the sigma as the mean values and the standard deviations to describe one 1D Gaussian distribution. And a Gaussian distribution comes with a probability density function, which basically returns the probability values for each data point within that continuous distribution. Okay, and the meanings for the mu's and sigmas are also clearly defined. Okay, all right, so it's how it looks like for a one-dimensional Gaussian distribution. Right, it's a very elegant and symmetric bell shape. Okay, so it's symmetric along this line of this mean value, right? So we can basically use the probability, the PDF function, the probability density function, to estimate the probability that the X falls into certain regions. So for example, in this case, the probability that a data point is smaller than the mean value is actually 0.5 if we compute the integrates of this PDF function. And for a function, for the probability that X should be lower than, for example, mu minus 1 standard deviation, we can also compute the region under that PDF function, which is, I think it's a very common mathematical tricks here. All right, and the Gaussian is actually ubiquitous. Like, say, a lot of the biological measurements, like the size, the physiological metrics from human bodies, if we take the logarithm of those variables, they will often show some Gaussian distributions. Okay, and the logarithm of the change rates, for example, the price, the stock market indices, they are also, people have found that there are a lot of Gaussian distributions in it. Okay, and in linguistics as well. Okay, so because it's so commonly observed in nature, and it's usually a very good tool to describe our data. Okay, so for example, if we have a Gaussian model, so now we first talk about a single Gaussian. We are not yet not there about the mixture Gaussians yet. We'll first talk about cases where there's only one Gaussian model. Okay, so for example, we use the mu and the sigma to describe a Gaussian distribution, right? So we should use them as separate as parameters. Okay, like the mu's and the sigmas are to learn from the data, right? And our assumption about the data is that the data are drawn from the Gaussian distribution. Okay, each data point is randomly drawn from the distribution, which means that they follow the probability density function. Okay, the probability of drawing some data points at a certain value is determined by the mathematical equation of the PDF function. That is our assumption. Okay, so because we're learning a model, the mu and sigmas are unknown, and we have to learn them from the data. And our task here is to find the parameters that best fit the data. Okay, so we have to define what is the best fit. Okay, And we will use this term, maximum likelihood estimation, right? We want to maximize the likelihood. I believe this term is something that you may already heard of in statistical classes, okay? All right, so let's use a very simple example of this maximum likelihood estimation, okay? So say the data is the weights of salmon fish, okay? And the assumption is that the weights is from a Gaussian distribution, and we want to estimate the mean values, the standard deviations of all salmon fish. Okay, so if we look at the distribution of data points, hey, it may look like this, right? It's a 2D, it's a 1D Gaussian distribution. So we can simply plot all the data points along this number scale, right? With this horizontal scale. So we want to estimate a Gaussian curve, okay? We want to decide what is the mean values, and what is the standard deviations, okay? So the mean value decide which center it is, right? And the standard deviations decide how thin and how wide that bell curve should be, all right? Okay, so what maximum likelihood estimation does is that we need to process each data point in our data sets, okay? We use the data points, the M data points, to fit a Gaussian model, okay? So for example, for the data point xi, by the definition of the PDF, the probability density function, we will have the probability for that data point xi, okay, given our parameters theta, and this which means theta includes mu and sigma, okay? So it's just a general notation for all the parameters in this case, okay? So the probability of observing xi given our parameters is described by this PDF function value, okay? So it is basically describes how likely it is to observe the xi given theta, okay? So we can assume that all the data points are independent, okay? So that means we can estimate the likelihood of the whole data sets by multiplying all the probabilities for each data points, right? We can multiply the likelihood function, the likelihood here for each data point, substitute into this formula, and to multiply over all the data points here, right? We just substitute the terms inside, okay? So this will be the likelihood of the whole data set, okay? So as the name indicated, we want to maximize this likelihood of the whole data sets. That is something we want to maximize, okay? And you know, to maximize this likelihood is not an easy thing, right? We need to do some mathematical transformation, right? Because the likelihood looks like this. If you use the L of L theta, it will be written like this, right? Which is basically the same thing as the previous slide. But it's easier to work with the log likelihood. You know, if we take a logarithm of some function, it will not change the direction of that function, right? It will be still ascending function will still be an ascending function, right? So we will take the logarithm of it. That doesn't change our goal. We need to maximize the log likelihood, right? But taking logarithm of some product will convert it into, you know, a summation, right? And also it will eliminate the exponential term. Okay, so we will have a bunch of things left like this, right? If we do the mathematics, right? That is the log likelihood. And our goal is to find the theta that maximizes the log likelihood. So now it becomes a very typical optimization problem, okay? And it is not constrained, right? It's a very simple one. So we just need to take the derivatives, right? We just take the derivatives of this log likelihood with respect to mu and the sigma, right? If you do this carefully, the derivative of the log likelihood with respect to the mu will be this one. And the derivative of the with respect to theta will be this one. And we want to make them 0 so that we can find extreme values. And by solving these two equations, we will have our solution that the mu should be the results of summing up all the values and divided by the quantity m. And the sigma should be the summation of the squares of the distance between each data points and the mu plus divided by 1/n and then square root of it. You see, so this is very, the statistics that we are very familiar with. These are the sampled means, right? Then the sampled variance of the data. Okay, so that's exactly how we're gonna measure the how we estimate the mu's and sigmas given a 1D Gaussian distribution, right? It's nothing fancy. It just we take the mean values of it, use it to estimate the mu, and we use the variance among data to use that estimate as the standard deviations. Okay. Oops. Okay. So we can and in statistics, if we want to be more strict in terms of our estimation, we should replace this one with the estimated values, which is this one. Okay, and then change that value to n-1, so that the variance, the estimate is unbiased. Okay, so that's how we get mu's and sigmas. That's all comply very well with our common sense, right? If we want to use the Gaussian distribution to describe the data, we can simply use this mean values and variance of data sets, of data points. Okay, so that's just one Gaussian, right? I think it's time to talk about the mixture of Gaussians, because eventually we want to use it to cluster data. Say if we have more than one distribution in our data sets, okay, which means we can extend our assumption. We can assume that our data are from multiple Gaussian distributions, right? If we have k Gaussian distributions, and then each Gaussian distribution has its own mean values, mu1, sigma1, mu2, sigma2, mu k, sigma k, right? So how do we generate the data? So we can imagine this, how the data are generated from multiple Gaussian distributions. We can think of it as 2 steps. First, we need to draw from k distributions with some probabilities, right? We need to select which distribution we use, right? So that will be decided by these k probability values, right? And then within each distribution selected, we need to draw a data from that particular Gaussian distribution, okay? So suppose that we selected the distribution J, then we need to draw a data point from that distribution J with mu J and the sigma J as our parameters. Okay, and this probability is just a simple 1D Gaussian distribution. Okay, and that's the basic principle of the assumption of mixture of Gaussians. Okay, so let's go back to the example. Say if we have 2 Gaussians, right? Our data are from 2 kinds of fish. Okay, and still we are measuring the weights, right, of salmon and the tuna fish, right? So this time, if we have all the data points here, we have a bucket of fish and the salmon and tuna are mixed together. So if we measure the weight for them and plot it on in the number scale, it'll be like this. It will, like, present some, it will show some patterns in the distributions. Say it's basically 2 mu's and 2 sigmas that we want to measure. You see? And the tricky thing is that how do we want to learn the mu's, the 2 mu's and the 2 sigmas? Okay. So to answer this, we will go back to the problem of how a data point is generated. Okay. We will follow the following process, right? We need to select Okay, the first step is to select whether this fish is salmon or tuna. Okay, so we will assign this step a probability. Say a fish has this phi of s probability to be salmon and the probability phi t to be tuna. Okay, that's our assumption. And these two probabilities needs to add up to 1 because we only have 2 fishes in our data, 2 kinds of fish in our data. Okay, and after this step is done, given the fish kind, then we can generate the data from the corresponding Gaussian distribution, right? For the phi s, for the salmon, we would have a salmon distribution, right, which is mu s and sigma s. And for the tuna, we will have a tuna Gaussian distribution. Okay, all right. So now I think the next from this slide on, the mathematics are a little bit more advanced. But not all of these are required, but I will go through it as, to make the story as clear as possible, okay? So how do we learn this is that we need to introduce some latent variables. So for example, these are the parameters, the model's parameters actually include these phi's, the probability for the salmon fish and the tuna fish, and the mean values, standard deviations for each fish. Okay, so that is the parameters in our model. Okay, so for each data points, we don't know if it is a salmon or tuna, so we will need to use some latent variable, which is zi, to indicate a latent random variable to indicate which distribution xi is from, right? So we first decide whether it's a salmon or tuna. Okay, so let's assume that zi equals 1 is for salmon and then zi equals 2 is for tuna. Okay, so the likelihood of xi, we can describe it with the summation of these 2 possible values for zi, right? Because zi has 2 possible outcomes, so we just need to enumerate all possible outcomes for zi and then use the summation for the PDL functions to represent the final total PDL likelihood function. Okay, and then we will need to use some further latent variable like qi to be the distribution of zi. So these are just for mathematical purpose, so that we can write these equations correctly. So the qi is the probability of zi, right? And the summation for all possible equal outcomes should be 1. And this is the probability of zi equals j. So this is just our mathematical languages here. Okay, so we can rewrite the likelihood into this form, right? We introduce some qi's, right? And the qi's is the conditional. So this probability is conditioned based on choosing qi. So these two actually eliminate each other, right? But since we want qi to represent the probabilities of zi, so we will deliberately introduce this latent variable. Okay, so we rewrite the likelihood, and the log likelihood of it, we can take the likelihood of the whole data sets, right? That's still we will convert basically the product into a summation, right? So the whole thing within the multiply function is this one, right? And then we take the log likelihood of it. We'll make the outside multiplication also into a summation, right? Into a summation here, and within it's a logarithm of a summation, right? A logarithm of a summation. We simply expand these parts into 2 items because we only have 2 possible outcomes, which is the salmon and the tuna. Okay, but it's difficult to take the derivative because it's a logarithm of a summation. Then we should do some more advanced mathematical tricks to change the log likelihood of this mathematical form into some kind of a lower bound of it. Okay, so let's just quickly skip this. I'm gonna skip this we simply need to convert it into some lower bound and estimate the QIs. Okay, so I think I can start from here. Okay. All right. So the new form of log likelihood, after we have switching from the original form to some lower bound, it will be like this. The log likelihood prime, it will be like this, and the phi of s. Okay. Yes. Yeah. So the final lower bound of the original log likelihood is written as this one. So we kind of make it a two items. The item left is for the salmon, and the item right is for the tuna. And we have this WS and the WT associated with each fish kind. Okay, and within the body, within the body of here, it is a pretty standard 1D PDF function for Gaussian distributions. Okay, so it's actually some additional parameters we need to estimate because we don't have WS and WT at the beginning. So now we need to consider WS and WT. And if we take the derivative of this, the log likelihood prime, and then we make the derivative with respect to mu s. So this is a similar thing that we did before, right? We'll make it 0, right? And by that, we can solve the mu of s. And by taking the derivative with respect to sigma, we can also solve the sigma of s. Okay. So now at this step, these two are very compact mathematical forms. Okay. So we don't need to look at the WS first, right? If we don't look at W first, then this whole summation is pretty much a mean value, right? It sums the xi's, but with some weights called WS, and normalized by the summation of all WS. And here it is the average. It is the weighted average of all the variance of data points, right? But weighted by the W of S and normalized by the summation of WS. Okay, and that also applies to the phi t. Okay, to the tuna fish. Okay, so the phi's of S and phi of t can also be solved by a constrained Lagrangian, using a constrained Lagrangian method. Okay, and the result is like we can use the mean values of S, WS to estimate phi of S, and the mean values of WT to estimate phi of T. All right. So if we put those results into one page, it'll be pretty much in this form. Okay. And now we can think of the meanings of these terms. Right. We have mu's sigma of S. So that is basically the distribution of the salmon fish. And this phi of S is the prior probability of being a salmon. Okay. And this is the Gaussian distribution of tuna. And the phi of T is the prior probability of being a tuna fish. Right. So, and within each term, there is a WS. And WS is something estimated by this way. Okay. So it's kind of the rule of probabilities. Okay. So the rule of Bayesian, the Bayesian rules of probabilities, that we need to use the likelihood of the so this is the posterior of the salmon given the data points, right? Which is the prior probability of phi of S, right? Times the likelihood of data given S, normalized by the two probabilities. Okay, so if you observe these two terms below, okay, so if you observe WS and WT, you can see that their denominators, they actually share the same value, okay? But the I think there's a typo here. This one really should be t. Otherwise, it's gonna be the same, okay? That is a typo. I will change that, okay? So this really should be t, okay? So these two probabilities, they add up to 1. And that is the posterior probabilities for being a 7 and a tuna. All right, so let's skip this EM algorithm of how, yeah, I'm not going to skip this because this is where we draw connections to the k-means algorithm, okay? All right, so summarizing all the previous slide here, what we're gonna do with a collection of data points that comes from 2 Gaussians, we're going to apply this expectation maximization algorithm, which is for EM algorithm. Okay, so we assume that they are from k Gaussian distributions with these phi's, and each distribution has mu and sigmas, right? You see, we randomly initialize all our parameters here, and we will repeat these steps until it's converged. The first step is called the E step, which is that for each data point, we will compute the expectation which distribution it is from, right? So the distribution, the expectation is estimated by this posterior probability that given the data points which the probability of that data points being to the J's distribution. What is the probability of that? And the distribution, the probability is estimated by the normalized likelihood, okay? The numerator is the likelihood times the phi of J, normalized by the summation of all possible J's, okay? For each J equals 1 to K, we compute the expectation, right? Which distribution it is from. You see, this is pretty similar to the first step of the k-means. In the first step of k-means, we need to paint each data point to either color, either red or blue, right? So that is a hard assignment, okay? But this expectation, which means that we can use a soft assignments that for each data point, we can use these probabilities to denote that I can paint these data points maybe 70% as red and the 30% as blue, for example. Okay, but they serve as the same function, right? It's kind of assignments for each data points to different distributions. Okay, so after the E step, next in the M step, in the maximization step, then we need to update all the parameters, and as if these posteriors are correct. Okay, we use them as correct values to maximize the likelihood, which is written in this way. Okay, we will maximize this likelihood, and we can then compute the updated values for each distribution. Okay, so this is what we have shown in the previous slide. The updated mu, the updated sigmas for each distribution. So, and for phi for each distribution. So the second M step is similar to the step in k-means that we compute the updated centroid positions, right? So you can think of this mu j and the mu sigma j. They are the kind of the centroid position for each distribution, right? And the shape of the distribution. So each data, so the updated values will be computed for each distributions, and we will repeat these steps until the algorithm is converged. Okay, so in this slide we just show an analogy to the k-means, right? In k-means we have E step, which is to assign each data point to a closest centroid, right? In the M step, we will need to update the positions of the centroids, but it's basically the same thing, similar thing in the mixture of Gaussian models. All right, let's use the rest of the time to cover a complete example. Let's continue this story of salmon versus fish, salmon versus tuna fish in this 1D Gaussian distribution, right? We have k equals 2, okay, because we have two Gaussian distributions to be estimated, okay? So for example, we have randomly initialized the parameters for salmon versus tuna, okay? So because it's random, then it's basically not informative at all. It could be at a random position, right? We have two Gaussian distributions in different colors. Okay, so what we can do, use these randomly initialized values, is that we, at the E step, we will take the data points out, and according to the randomly initialized parameters, we can compute the posteriors for that data point, which is the probability that data point, that black data points, belongs to salmon versus belongs to tuna. Okay, so in this particular example, because our data point X here is closer to the orange distribution and the farther away to the blue distribution. So the computed results will tell us that the posterior probability being a salmon is larger, which is 0.6, as opposed to the posterior being a tuna as 0.4. Okay, so that means it's more likely to be a salmon, right? And then we can use this we should compute this for all the data points. Okay, so we can imagine that all the data points that is to the left of this black data points, they all should have larger values in WS because they are nearer to the orange center, to the orange distribution, right? So compared to all the data points towards the left, towards the right, and all the data points on the right, they should tend to have larger posteriors FW as tuna fish. Okay, and then after the E step is done, we need to do the M step, which is to update the parameters for each for salmon and the tuna. Okay, so we use that to compute the new mean values for S and the T, and also for the we should also update the sigmas. Okay, so imagine that after the first round, that's new values for mu of S will basically pull this orange distribution towards the left. Okay, because the majority of data points are here, right? The data points that have larger weights, have larger salmon weights, lying at near the left side, while the data points that have larger tuna weights, they are lying at the right side, right? So after the results of the M step, the two distribution will got pulled towards the two ends. Okay, so we can imagine that these two are getting closer to are getting apart because they need to update it to the new positions. Okay, so that is after one iteration, and in the next iteration we should do the same thing, right? We should compute the posteriors. For example, in this case, the difference is getting larger because that data point is closer to the relative distance. The relative difference between the distance is larger. Okay, so the probability of being a salmon is even higher than the tuna. Okay, so we will repeat this step until the positions and the shape of these two Gaussian distributions stabilize in our data sets. For example, it could be like this. So after the distribution is after the estimation is converged, we will have two stabilized Gaussian distributions. Okay, and you see here I painted all the data points with different colors, with different transparency. Yeah, so because the data in the middle, they are both these parts, these data points, for example, they are very far away from the centroids, from the central position of the two Gaussians. So the probabilities for them, for this one being a tuna, actually is not as high as those ones near the near these positions. All right. So for example, the data point here, it could be a 77%. Let me clean up a bit. It may be 77% being a salmon, right? But we don't totally eliminate the possibility that it is also 23% being a tuna, okay? Although biologically it doesn't make sense, but you know, if we have other cases that a fish can have a data point can have overlapped clusters. It's very useful, and also it's useful to get these numbers, right? It tells that how confident our model is, right? It gives a number to say that we have this 77% as our confidence to assume that it is a salmon fish. Okay. And it's different from the hard assignments of k-means. All right, so another example, the last example about multivariate Gaussian is something we can quickly go through. I will go to the last slide, okay? It's like given a distribution in 2D space, right? We just randomly initialize some Gaussian distributions. It could be like this. And for each xi, we need to compute the posterior, similar to a 1D case, right? And the data here towards the left, right? They will have larger posteriors to this blue distribution, right? So that means after one round of EM algorithm, the two distributions will be moved towards the desired position, okay? So eventually we will fit two Gaussian distributions like this. Okay, and all these data points, they will be assigned with two probabilities, either being one probability or either being one distribution versus the other one. Okay. Yeah, so I think that's pretty much for the 2D Gaussian, for the mixture of Gaussian models, and we are almost done with the clustering. Oh, I see a question. What does EML standard for again? So the maximum likelihood estimation, yeah, the MLE. Yeah, maximum likelihood estimation. Right. Okay, so yeah, we have some algorithms in the middle, which is the the hierarchical clustering and the connectivity-based clustering DB-scan, which I think are classical examples of clustering algorithms. We can probably talk about that on next Tuesday's class. But we are pretty much done with the clustering algorithm today. And in the homework, we will implement a k-means algorithm and just run it with a toy data sets. Okay. All right. That's pretty much for it today. Thank you, guys. I will see you next week.